Hello viewer, in this video we will learn about the various applications of steady flow energy equation. If you are interested, sit relaxed, make yourself comfortable, watch, enjoy and learn. Over to the topic now. The first device that we are going to learn is a turbine. Turbine delivers power. It can give us work. When you say turbine as a steady flow device which can deliver work, our aim naturally is to question how much work can it deliver. To answer this, we are going to make use of steady flow energy equation. First, the schematic of a turbine is shown here. Mass can enter the turbine and mass can flow out of the turbine, and it can deliver work. So this is a shaft. The turbine is capable of delivering us shaft work. Since it is a flow system, normally a control surface is put around it, or the control volume. In order to know or find out how much power this turbine can deliver, we consider two sections, 1 and 2. 1 is at the inlet, 2 is at the outlet. Apply steady flow energy equation at these two sections. What this steady flow energy equation says, total energy is conserved. That means the energy at section 1 is equal to the energy at section 2. And we know the steady flow energy equation is Q dot in plus W dot in, or the heat input or the heat at the inlet and work input to the turbine. M1 dot is the mass that enters. H1 is the enthalpy the mass carries at the inlet. C1 is the velocity of the mass at the inlet. Z1 is the elevation of the inlet 1 or the section 1 from an arbitrary reference. So on the right hand side of the equation are the corresponding terms at the exit or the outlet of the turbine. In this equation, we neglect kinetic and potential energy. We assume the velocity of the mass at the inlet and outlet are negligible or they are equal, and hence they can cancel it out. Similarly, Z1 and Z2, the elevation are same from the arbitrary reference, and hence we can cancel kinetic energy and potential energy terms. And for a turbine, there is no work input. Of course, it delivers work output. There is no work input, and hence we can neglect W in. And the turbine is perfectly insulated. It is perfectly insulated, and hence there is no heat transfer. Therefore, Q dot in and Q dot out are cancelled. So what is remaining? M1 dot H1 is equal to W dot out plus M2 dot H2. And of course, M1 is equal to M2, which is equal to M dot, because turbine is a steady flow device. Accordingly, we can rewrite the equation like this, and from this, on rearrangement, we get what is the work output from a turbine. So M dot H1 minus H2 is the final expression to calculate the work output from a turbine, also represented using the symbol W suffix T. So H1 and H2 are the enthalpies at the inlet and the outlet. The next device we are going to learn is compressor. Compressor requires work input in order to compress a system or compress a fluid. We need to spend energy. So that energy is the work input. The question obviously is how much work input is required by the compressor. That we are going to derive using steady flow energy equation. So compressor is just a reverse of a turbine. Schematic of a compressor. So there is mass in, mass out. It requires work input W suffix C. So there is a shaft. We need to give, or we need to input shaft work. And in order to derive an expression for WC, consider two sections 1 and 2 at the inlet and exit, and apply steady flow energy equations. The equation between 1 and 2, and this is the equation. Once again, neglect potential and kinetic energies. So these two terms will go off on both sides of the equation. Compressor doesn't deliver work. It requires work from us. Therefore, work out can be neglected. Again, the compressor is perfectly insulated. Therefore, there is no heat transfer, and hence Q dot in, Q dot out are neglected. So what is left? Once again, M1 dot, M2 dot are equal, and hence we can rewrite the equation like this. And on rearranging, we are able to find out what is the work input required by the compressor, also denoted by the symbol W suffix C. So the third device we are going to learn is a nozzle. A nozzle increases the velocity of a fluid by drop in pressure. In order to increase the velocity of the fluid, we use nozzles, which finds application in turbines, rockets, jet propulsion. The schematic of nozzle is shown here. Some mass is entering, the same mass is leaving. It enters with the velocity c1 and leaves with the velocity c2. Of course, c2 is greater than c1 because nozzle increases the velocity. Usually a nozzle is insulated. In order to analyze what is the exit velocity, what is the exit velocity, that is c2, consider two sections by putting a control surface. So in order to analyze, we need to put a control surface, and two sections 1 and 2 are considered. Apply steady flow energy equation between 1 and 2. That equation is this one. Once again, neglect potential and kinetic energies. Therefore, we cannot neglect the kinetic energy here. We can neglect only potential energy because the purpose of a nozzle is to increase the velocity. Therefore, kinetic energy term remains. So we can assume the inlet and the exit are at the same level, and hence we can cancel out Z1 and Z2. There is no work input and output in the nozzle, and hence this W dot in and W dot out both can be cancelled. It's perfectly insulated. There is no heat transfer. So what is left out is, and M1 dot M2 dot are equal. Therefore, we can write like this. So this equation can be rearranged like this. This again can be rearranged like this. What is our aim? Our aim is to find out C2, what is the increase in velocity, and in comparison with the C2, C1 is very low, and hence in general C1 is neglected. Upon rearrangement, this C2 is equal to 2 multiplied by square root of h1 minus h2. So the final velocity C2 is equal to 2 into square root of h1 minus h2. So the next device we are going to learn is a diffuser, which increases the pressure of a fluid by reduction in velocity. It's just a reverse of a nozzle where the nozzle increases the velocity by reduction in pressure, but here it increases the pressure by reduction in velocity. The schematic of a diffuser is shown here. And put a control surface and consider two sections 1 and 2. Apply steady flow energy equation between 1 and 2. So the final simplified form is given here directly, because in the past 2 or 3 slides we learned how this final step is arrived at. I don't want to repeat. C2 is negligible because there is a reduction in velocity. Therefore, H2, it is a enthalpy, is equal to half C1 square plus H1. So because of the diffuser, final enthalpy increases, which is an indication of increase in pressure. The next device is a heat exchanger. A radiator used in the four-wheeler, a car or a bus or a truck, is a heat exchanger. So heat exchanger is a device in which heat is transferred from one fluid to another. A schematic of heat exchanger is shown here. So some cold fluid is flowing in, and when it comes out, it is hot. But the mass flow of the cold fluid is equal. That means there is no accumulation of mass inside this. And there is another stream. There is a hot fluid. The hot fluid flows through this and it comes out. When it comes out, it goes as a cold fluid, but the mass remains the same. And note, there is no mixing of these two fluids inside this heat exchanger. There is no mixing. Hot fluid flows in one chamber, cold fluid flows in another chamber, and the heat transfer is due to the conduction, radiation. There is no mixing of these two fluids. And observe the color of this chamber. It is hot, somewhat red. And here at this end, it's a light blue, and here it is a dark blue. If you pass the hot fluid and the cold fluid through these, observe, here it is hot. When it goes out, it goes as a cold fluid. Here it is cold. When it goes out, it becomes hot. That means heat is transferred between the two fluids. So put sections 1 and 3 for the cold fluid and 2 and 4 for the hot fluid. Enclose them in a control surface, and here two fluid streams are involved. So this is the control surface. We are going to apply steady flow energy equation for the control surface. The final simplified expression is given m dot c h1 plus m dot h h2 plus m dot c h3 plus m dot h h4. So m dot c stands for cold fluid, m dot h stands for hot fluid, h1 represents enthalpy at section 1, h2 represents enthalpy at section 2, and these three, sorry, h3 and h4 represents enthalpies at section 3 and 4 respectively. And remember, this equation is arrived neglecting potential energy, kinetic energy, assuming no work done, assuming no heat transfer. So this can be rearranged like this, and this is the final expression for a heat exchanger. So m dot h is on the left hand side of the equation, m dot c is on the right hand side of the equation. What it implies is there is an energy balance between the hot fluid and the cold fluid. This can be rewritten like this. So the next device is throttling device. So what is this throttling device? It is a flow restricting device that causes pressure drop. It restricts the flow, which is accompanied by a pressure drop. And the schematic is nothing but an adjustable valve. Put a control surface or control volume around this valve and consider two sections 1 and 2 at the inlet and the outlet. Apply steady flow energy equation. No kinetic energy and potential energy. Therefore, these two terms gets cancelled. No work and heat transfer. Therefore, this also gets cancelled. What it implies is H1 is equal to H2 because M1 dot is equal to M2 dot and it is a steady flow. Therefore, H1 is equal to H2, which represents there is no change in enthalpy. Enthalpy H is equal to U plus PV. U is the internal energy, PV is the flow work. So it's a flow device. Some flow work is involved. Then how we are saying H1 is equal to H2? H1 equal to U1 plus P1 V1, H2 equal to U2 plus P2 V2. So U1 may be equal to U2, but flow occurs. How this P1 V1 is equal to P2 V2? And this process is called a throttling process, and the device is a throttling device. So throttling process is the one in which enthalpy is constant. H is equal to U plus PV. And now we are answering. If flow work PV increases, if P1 V1 is not equal to P2 V2, if there is an increase, then the internal energy U decreases with a corresponding drop in temperature of the system. Remember, internal energy is a function of temperature only for an ideal gas. So internal energy decreases with a corresponding drop in temperature of the system. One application of this throttling device is found in refrigeration system. So throttle valve or a throttling device in a refrigeration system reduces the internal energy with a corresponding drop in temperature of the system, but it maintains the enthalpy. But it maintains the enthalpy.
So, what is the takeaway in this lecture? Of course, we applied steady flow energy equation for different devices like a turbine, compressor, nozzle, diffuser, heat exchanger, and a throttle valve. How this general steady flow energy equation is simplified for these devices are given here. One need to apply these formulas to solve numerical on the devices discussed. Thank you.